In this screencast, I want to prove that Prim's minimum spanning tree algorithm is correct. And to do that, I need to prove something called the cut property. So what does the cut property say? Cut property says that given a weighted connected graph, G equal to V, the vertices, and E, the edges, we're going to assume that all the edge costs are distinct. Again, this is not a big assumption because even if two edges have the same cost, it's easy to just change one by a little bit without really changing the problem that you're working on. And in this graph, we're going to pick a non-empty proper subset of the set of vertices. So in other words, S is going to have some vertices in it, but not all the vertices. And in addition to that, we're going to assume that E represents an edge from S, which is on this side, to V minus S, capital V minus S. So in other words, it crosses the boundary between the edges, the vertices that are in S, and the vertices that are in V minus S. If E is the minimal, the smallest weight edge that does that crosses this boundary, then we want to show that every minimum spanning tree must contain E. So that's what the cut property says. That if you have a minimal cost edge between two sets like this, then it must be in the minimum spanning tree. So keep this picture in mind and refer back to it when I go to the next slide and actually do the proof. But this is the basic idea. You'll see we're going to have this minimal spanning tree which is pictured here. Both sides, it covers all the vertices in V, and it's going to contain some edge, E prime, that crosses this boundary, and I'll show you why on the next slide. And then we're going to replace that with this new E that is the minimum cost edge. But more on that on the next slide. So here's the proof of the cut property. We're going to do a proof by contradiction. So I'm going to try to go over this kind of slow because you might not be familiar with or recently done a proof by contradiction. Suppose that T is a minimum spanning tree for our graph, and it doesn't contain E, where E is the minimal edge between S and B minus S. We're going to show that this leads to a contradiction. So this is the setup. We're assuming two things here, that we have a minimal spanning tree and it does not contain E, where E is a minimal edge between these two sets. What we're going to do is we're going to find that these two things just can't both be true. They're going to lead to a contradiction. So how do we do that? Well, we want to find an E prime, refer back to the last picture, the last slide, in T, so that exchanging it E for E prime creates a new spanning tree, T prime, with less cost than T. Okay. So how do we do that? Well, again, if you look back at the picture, if we add E to T, that will create a cycle. Okay, because remember, T was a spanning tree, which means that there's an edge from any vertex V to any other vertex W. So we've got a path from V to W, and by adding E, which connects V and W, we're going to get a cycle. Okay. If we follow that path around, you might want to refer back to the last slide, if we follow that path around, we'll find that there has to be an edge between S and a different edge than E between S and S minus. Oh, this should be V minus S. Sorry, this should be V minus S. There has to be an edge between those two sets. Why is that? Because the cycle that we created starts out in S, right, moves to V minus S, wanders around, but somehow it's got to get back to V, the initial vertex on the edge. And in order to get back to V, it has to cross back over into S. So finally, let that edge this new edge that we found that goes from S to V minus S, let that new edge be E prime. Remove it now from T with this edge E, and we'll get a new T prime. So what we've done is exchange the edge E for the edge E prime. And by doing that, we still get a spanning tree, okay? But the key thing is, notice this spanning tree has a lower cost. Why does it have a lower cost? Because the weight of the edge of E is less than the weight of the edge of E prime. So I'd suggest writing down a shorthand version of this argument and then going back and looking at the picture and make sure you see how it works. So finally, we're ready to do a proof of that Prim's algorithm is correct, namely that Prim's algorithm produces a minimum spanning tree. And again, we're going to do this by proof by contradiction. Assume that Prim's algorithm does not give a minimum spanning tree. Okay? Well, then take a minimum spanning tree for the graph, for the weighted graph, and since Prim doesn't give a minimum spanning tree, at some point, as Prim's constructing its sequence of trees, right? That's what Prim does. It constructs a sequence of trees, Ti. At some point, it must disagree with the minimum spanning tree at M. So at some point, there must be a tree that has an edge that's not contained in the minimum spanning tree. Okay, so this would be the first one of those as it's growing to contain an edge that's not in the minimum spanning tree. But now we're done if you think about it, because now what we'll do is we'll apply the cut property to the vertices in TK and V minus the vertices in TK. Okay, we know that the minimum cost edge from TK to V minus TK must be in the minimum spanning tree. That's what the cut property says, after all. But Prim's algorithm chooses that particular edge, that minimum cost edge, by the definition of the algorithm. That's how it works. It picks the minimum cost edge between two sets, namely the set of vertices that are in the existing tree, in this case TK, and the set of vertices that are not in the last tree that it constructed, so V minus TK. Therefore, TK must have the same edges as there are in the minimum spanning tree, because the edge it picked is the least cost edge, and we know that by the cut property, the least cost edge must be in the minimum spanning tree. So this contradicts the premise that Prim's algorithm does not find a minimum spanning tree. And we're all done. So that's all there is to it. Good luck. I think it takes a while to understand this, and it's worth going through it a couple of times until you get it.